Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action. The subject of this lecture is the symmetric group of degree n Sn and the cycle notation for it. Before formally studying groups, we like to have examples. A group is a non-empty set, and it has one operation. There's a way of combining two elements and getting another element of that set. And that operation we usually call multiplication. That operation has to be closed, meaning that if you take two elements and multiply them or apply that operation, you get another element of that set. It has to be associative. XY times z should be x times yz. There should be an identity element. There should be some element that when you multiply by anything, nothing happens. And every element needs to have an inverse, a friend that if you multiply the two together, you get the identity. The reason for studying examples is we want to have some very concrete objects that are groups that we are familiar with so that we can look for patterns. When a question comes up, we can go back to it and try to hone our intuition and try to figure out, could such a thing possibly be true? And when we are trying to prove things, if you have an idea that maybe we can prove this or that way, we can apply to examples that idea, that technique, see if it actually works. Having a set of examples is a very useful thing. Some examples are the dihedral groups. Those are symmetries of polygons. In the previous video, we looked at D8 symmetries of a square in some detail. Another one is integers mod n, and that's also a subject of another video. Another one is permutations on a set omega. If omega is any set, the permutations on it, all one-to-one onto functions from omega to omega, they form a group, and that was the subject of a whole video all by itself. In fact, the group we will be looking at today will be a special case of Perm omega. Another one is GLNF, group of invertible n by n matrices over a field. If you don't know what those things mean, don't worry about it. Watch the video about it. In this video, we are going to be talking about the symmetric group of degree n. What is Sn? Is the set of permutations of n elements. Our generic set with n elements is bracket n, that includes 1 through n, and the set of permutations of that is Sn. It's the set of one-to-one onto functions from bracket n to bracket n. This is an example of permutations of a set, and so we actually already know that Sn is a group. One of the important things we will do in this lecture is we will introduce cycle notation for the elements of Sn. Some of these groups are groups that you really want to get to know intimately. S3 and S4 are two such groups. S3 in particular will be a group that we will talk about in some detail. When someone says permutation, what comes to mind is a different way of arranging elements where the order matters and you put the elements you have in some particular order. 3, 4, 1, 2 would be a permutation of 1, 2, 3, 4. One possible way of arranging them. But you can also think of this permutation in several different ways. One way to write that 3, 4, 1, 2 is to write it in this two-line notation with 1, 2, 3, 4 on top. That would tell you that we have this original order in mind, 1, 2, 3, 4, and now we have put things in different order. In the spot for 1, we have put 3. In the spot for 2, we have put 4. In the spot for 3, we have put 1. And in the spot for 4, we have put 2. That sort of makes it clear that we've got a permutation of 1, 2, 3, 4. But if we write it like this, then we can also see that a permutation is a one-to-one onto function. 1 went to 3, 2 went to 4, 3 went to 1, 4 went to 2. And we can draw that function. 1 is going to 3, 3 is going to 1, 2 is going to 4, 4 is going to 2. So a permutation is a one-to-one onto a function from a set to itself. In group theory, we use the cycle notation, which I will give you a quick example now, but I will get into a little bit more detail later. This permutation 3, 4, 1, 2, instead of thinking of it as moving things around, you might want to think of the fact that what it's really doing is switching the place of 1 and 3 and switching the place of 2 and 4. So it has two cycles. And the way we write that is 1, 3, 2, 4. When we write 1, 3, that means that you switch the place of 1 and 3. When we write 2, 4, that means switch the place of 2 and 4. Let me just define Sn one more time. So bracket n is 1 through n. This is a set with n elements. And Sn is the set of functions from bracket n to bracket n that are bijections. That means they're one-to-one and onto. If you don't know what one-to-one and onto is, watch my video on one-to-one onto functions. Elements of Sn are called permutations, permutations of bracket n. This is called the symmetric group of degree n. So the n is not the size of the group, is the size of the set that's being permuted. Again, I'm repeating myself, even if you have an infinite set, the set of one-to-one onto functions from omega to omega, I have been calling perm omega. For this perm, the operation was function composition. If you have f and g in perm, that fg is f circle g is the composition of g and f. That means do g first, then f. And with that operation, perm omega is a group. It's closed, it's associative, it has an identity, and it has inverses. Again, the subject of a previous video. And Sn is an important special case. How is it a special case? It's just that we are making sure that the set omega is a finite set. We're looking at permutations of finite number of things. So Sn is also a group because it's a special case. But we want to think about Sn slightly differently and on its own terms. Let's start with that cycle notation. So here I've got a permutation of 7 things. 3, 7, 5, 4, 1, 6, 2 is a permutation of 1 through 7. The way we can think about that is that in the first spot, we put 3, in the second spot, we put 7, and so forth. And we can write that in a 2-line notation in the following way. In the first spot, we put 3, in the second spot, 7, in the third spot, 5, fourth spot 4, and so forth. We can also think of this as a function. 1 goes to 3 because this 1 goes to 3. What's in the first spot? 3. So 1 going to 3 is telling me that. You could also write this as a function. 3 goes to this first spot. If you do that, then you'll get the inverse of the one that I'm writing, and that would be just as fine. 2 goes to 7, 3 goes to 5, 4 goes to 4, 5 goes to 1, 6 goes to 6, and 7 goes to 2. This would be another way of thinking about it as a function. As cycles, we can also look at that function and see where every element is going. Where does 1 go? Well, 1 is going to 3. Then instead of switching to 2, we can follow with 3. See, where does 3 go? 3 is going to 5. And where's 5 going? 5 is going back to 1. So I have a cycle of length 3. I have a 3 cycle. 1 goes to 3, 3 goes to 5, 5 goes to 1. So in this permutation, you are switching the place of those 3 things. 1 to 3, 3 to 5, 5 to 1. The first element that we haven't taken care of is 2. So what is happening to 2? 2 is going to 7. Where's 7 going? 7 is going back to 2. So there we have a 2 cycle, a cycle of length 2, what's called a transposition. Have we taken care of everything? No, we haven't done anything with 4 yet. What happens to 4? 4 is going to 4. So 4 is not going anywhere. 4 is a fixed point. And the only other element left is 6, and that's also a fixed point. So this diagram of cycles tells us what this permutation is doing. It's taking 1 to 3, 3 to 5, 5 to 1, switching the place of 2 and 7, and fixing 4 and 6. To group this is the best way of writing a permutation, except if n is large, it's not practical to actually draw them. What we do is we write each of these cycles in parentheses. We start with the parentheses. Where does 1 go? Well, 1 goes to 3. Where does 3 go? 3 goes to 5. Where does 5 go? Back to 1. When you go back to 1, you close your parentheses. So when we see this 1, 3, 5 in parentheses, we group theorists think 1 goes to 3, 3 goes to 5, 5 goes to 1. And then we say, well, what's the first thing that we don't know about? Well, that's 2. Where does 2 go? 2 goes to 7. What happens to 7? 7 goes back to 2. What else is left? There's 4. Where does 4 go? Back to 4. So close the parentheses. Where does 6 go? 6 goes back to 6 also. So close that parentheses. Usually we omit the fixed points and just write 1, 3, 5, 2, 7. So in cycle notation, that permutation will be written as 1, 3, 5, 2, 7. If you want to emphasize the fixed points, then you will write them. You might write them as 4 and 6. For example, this might be an element in S9, and 8 and 9 were also fixed. In that case, you might want to write those down so that we know that there were 9 things that were permuted. It's just that the final ones were fixed. But in general, the most common thing is to drop the fixed points. A few vocabulary. If n is a positive integer, Sn the symmetric group of degree n, tau is an element of Sn, and tau happens to do the following. It sends A1 to A2, A2 goes to A3, A3 goes to A4, all the way till AM, and AM goes back to A1. And tau fixes every other element of n, so it just has one cycle. In that case, write it as this one cycle, A1, A2, A3 through AM, parentheses closed, which means that AM goes back to A1. This is called a cycle of length M, or an M cycle. M stands for how many things are in the cycle. Any element of Sn, as we saw in the previous example, is a product of disjoint cycles. You just start with one element and follow through where it went, and eventually you'll have to come back because there's a finite number of elements, and you might have got everything, in which case you are done with one cycle. But if not, you start with whatever is left and you get another cycle, another cycle, eventually you'll get everything. So every element of Sn can be written as a product of disjoint cycles. When I say product, I think we can write a combination of disjoint cycles, and disjoint means that there's no repeats, there's no numbers that appear in both of them. This is called the cycle decomposition of sigma. If you write sigma as disjoint cycles, then they will have different lengths. And if you start with the smallest length, n1, n2, and go all the way to nr, if those are the lengths, including the one cycles, then this list of numbers, which are the lengths of the cycles, is called the cycle type of sigma. For example, the element we have been looking at in S7, the 3-cycle 135, and then a 2-cycle 27, I'm thinking this as a product of these two. Cycle type of this guy is 1, 1, 2, 3. There's two cycles of size 1, those were the 4 and 6 that were fixed. Then there's a cycle of length 2 and a cycle of length 3. Usually we write that as 1 squared comma 2, 3. That same element, you can think of it as an element of S9. The 13527 could be an element of S9, in which case its cycle type is different, because then it has 4 fixed points and then a cycle of length 2 and a cycle of length 3. So cycle type depends on the context, depends where you are, what the cycle type is. Let's look at another example. This is a 2-line permutation for something in S9. First, the cycle decomposition of sigma. How do I do that? I start with 1. Where does it go? 1 goes to 2, so 1 goes to 2. Then at 2, where does 2 go? 2 goes to 6, so 2 goes to 6. Where does 6 go? So now I go over here, 6 goes back to 1, so I close my parentheses. What's the first thing that I haven't taken care of? It's 3. Where does 3 go? 3 goes to 4. And where does 4 go? 4 goes back to 3, so you close the cycle. What's the first thing that I've not taken care of? It's 5. Where does 5 go? 5 goes to 7. Where does 7 go? 7 goes to 8. Where does 8 go? 8 goes to 9. And where does 9 go? Back to 5. Now I'm done. I've got everything and I don't have any fixed points. This is the cycle decomposition of this element sigma. And the cycle type is 2, 3, 4, because there's one cycle of length 2, one of length 3, and one of length 4. Let's talk about multiplying permutations. Permutations are bijections. They're one-to-one onto functions. And so the way we multiply them, just like we multiply one-to-one onto functions, is via function composition. Let's look at an example. We have two elements of S5 here, 1, 4, 2, 5, a 4-cycle, and 3, 5, 2, a 3-cycle. And these are two permutations in S5. And the question is, what's 1, 4, 2, 5 times 3, 5, 2? You have to remember, when you're multiplying functions, the way those functions are composed, you do the right-handmost function first, and then you do the next one, f of g of x. G gets done first. Here, let's see what these functions are. The first one we have to apply is 3, 5, 2, and it's a function on 1, 2, 3, 4, 5. So we can actually draw exactly what it does. 3 goes to 5. Where does 5 go? 5 goes to 2, and 2 goes back to 3. What about 1 and 4? They are fixed. 1 goes to 1, and 4 goes to 4. So this is the 3, 5, 2 function, which we need to do first. Now we need to compose that with 1, 4, 2, 5. And that's another function from 1 through 5 to 1 through 5. What does that do? 1 goes to 4, 4 goes to 2, goes to 5, and 5 goes back to 1, and 3 is a fixed point. These are the two functions, and composing them just means do one, then do the other. And what do you get? You get another one-to-one onto function from 1 through 5 to 1 through 5. Where does 1 go? 3, 5, 2 sends 1 to 1, then 1 goes to 4. And so the resulting thing is that 1 goes to 4. In the product, 1 goes to 4. What about 2? 2 goes to 3 in the first one, and then 3 is fixed. So 2 goes to 3. And we can now continue that. For example, what happens to 3? 3 goes to 5, and 5 goes to 1. So 3 goes to 1. What happens to 4? 4 is fixed, but then it goes to 2. So 4 goes to 2. What about 5? 5 goes to 2 and then back to 5. So actually in the product, 5 is fixed. So there it is. There is the product, and we can now actually write it in cycle notation if you like. It's 1 goes to 4, 4 goes to 2, 2 goes to 3, 3 goes back to 1, and 5, which we haven't written, is fixed. The result is that 1, 4, 2, 5 times 3, 5, 2 is 1, 4, 2, 3. Again, don't get confused by the order. This is the product of these two permutations, but when we think of them as functions, 3, 5, 2 goes first. We could do this product without drawing. You could just start here and say, well, where does 1 go? And you start with the permutation on the right, and you say, where does 1 go here? 1 goes to 1, and then what does happen to it? 1 goes to 4, so 1 goes to 4. 4 goes to 4, and then 4 goes to 2. Where does 2 go? 2 goes to 3, 3 goes to 3, so 2 goes to 3. 3 goes to 5, and then where does 5 go? 5 goes back to 1. The only thing left is 5, and you might check that. 5 goes to 2, 2 goes to 5, and so 5 is fixed. Let's just do one more without drawing. Let's multiply 134 by 243. How do we do that? We do 243 first, then 134. We say, where does 1 go? In 243, 1 goes to 1. 1 is fixed. So 1 goes to 1. Then we go here, 1 goes to what? It goes to 3. So the resulting thing is that 1 goes to 3. Now we worry about 3. We don't worry about 2 yet. We worry about 3. We start here. Where does 3 go? 3 goes to 2. Where does 2 go? 2 is fixed. So 2 goes to 2. So the resulting thing is 3 goes to 2. Now we worry about 2. 2 goes to 4, 4 goes to 1. So 2 is going back to 1, and we close the parentheses. And the only thing left is 4, and 4 got to be fixed, but you can check that anyway. 4 goes to 3, and 3 goes back to 4. If you multiply it the other way, 243 times 134, where does 1 go? Well, 1 goes to 3, then 3 goes to 2. So 1 goes to 2, 2 goes to 2, and then 2 goes to 4. And where does 4 go? 4 goes to 1, and 1 goes to 1, so 4 goes back to 1. And you can check that 3 is fixed. 3 goes to 4, 4 goes to 3, and we're done. What's the order of Sn? How many elements does Sn have? When you put absolute values around a set, we're talking about its size, how many elements it has. What's the order of Sn? These are one-to-one onto functions from n things to n things. Where can I send 1? I can send 1 to n places. But after I've sent 1, I can't send anything more to that place because it has to be one-to-one. So 2 has n-1 choices, and 3 has n-2 choices. 4 has n-3, and so on. You just keep going down. The number of choices you have is n times n-1, n-2, all the way to 2, 1, n factorial. So Sn, the permutations of bracket n, is a group of order n factorial, and it's called the symmetric group of degree n. So what does it mean to be a group? It means that we have an operation. What's the operation? This multiplying of permutations that we were just talking about, which is basically function composition. And what about it? It's closed. When you take 2 permutations and multiply them, you get another permutation. It's associative. If you do one, then another, if you got to do 3 of them in a row, it doesn't matter if you do these 2 first and then multiply it by the third one, or multiply the last 2 and then multiply the first one by it. This product is not commutative. You can't switch them. We saw an example right up here. 134 times 243 was different than 243 times 134, but it is associative. The map that sends everything to itself, that's the identity map, and every element has an inverse. So this is an example of a group. Permutations form a group. Now we want to think about just S3, permutations of 3 things. That has 6 elements because 3 factorial is 6, and this is a pretty good group to get to know. It's the smallest group where the multiplication is non-commutative, and over time you want to be really friends with this group S3. What are its elements? These are one-to-one onto maps from 1, 2, 3 to 1, 2, 3. One element is the identity element, which in every group I denote by E, but you could also call this 1 if you like. This is the map that sends 1 to 1, 2 to 2, 3 to 3. Here's another map. This is the map that sends 1 to 2, 2 to 3, 3 to 1. This is a cycle, a 3 cycle, 1, 2, 3. I want to do algebra, so I want to give names to these. This guy I'm going to call F. So F is 1, 2, 3. The next thing I want to do is find F squared. So what's F squared? That's F times F. That means what happens if I do this permutation twice in a row? So 1 goes to 2, but then 2 goes to 3. So 1 goes to 3, and then 3 goes to 2 because 3 went to 1 and 1 went to 2, and 2 went to 3 and 3 went to 1. So 2 goes to 1. So this is F squared. And what it is another 3 cycle. 1, 3, 2. 1 goes to 3, 3 goes to 2, 2 goes to 1. Now, what's F cubed? If you think about things sitting around the 3 cycle, if you do it 3 times, everything is back to where it started, and you get identity. So F cubed is E. That's one thing to remember. But there's 6 elements, so I pick another one, the one that fixes 3 and switches the place of 1 and 2. So this is 1, 2. It's just a 2 cycle, and I'm going to call that G. Now, G squared, because it's just a 2 cycle, G squared is going to be identity. So I'm not going to get any mileage out of just squaring G. but I can multiply G by F. I can do FG. That means do G first, then F is 1, 3. If you do G first, 1 goes to 2, then 2 goes to 3 in F, and so 1 goes to 3. You can see that 2 is going to be fixed and 3 goes back to 1. So that's another element. And finally, I can do F squared G, and that'll be 2, 3, but that's also GF. So that's another thing to remember. These are the 6 elements of S3, the symmetric group of degree 3. So S3 is permutations of 3 things, and we have now seen that it can be represented in several different ways. We can think of it as a group of permutation. When we say that, that means that we're thinking of them as these. There's 2, 3 cycles, 1, 2, 3, 1, 3, 2, and there's 3, 2 cycles, 1, 2, 1, 3, 2, 3, and 1, 1 cycle, the identity. And this is a really nice way of writing it, because if you want to multiply things, you just use multiplication of permutations that we have seen. Sometimes you want to do algebra, and in which case you might want to write it in terms of the F and G that we had. The elements that we found are E, F, F squared, G, F, G, and F squared G. But I have got to write down these relations. The relations are F cubed is identity, G squared is identity, and GF is the same as F squared G. These are the relations that I need, because using them, if you write any word, I can simplify them. Whenever I see 3 F's next to each other, that's F cubed, that's E, that goes away. And whenever I see 2 G's next to each other, they cancel and go away. And if I see GF, I can bring F to the other side, but with a price. And the price is that it becomes F squared. So with that, I can switch the place of F and G whenever I want to, so as to have all the F's together and all the G's together and combine them to see what the result is. The shorthand way, maybe our favorite way of writing it, is using generators and relations, is to write that S3 is the group generated by F and G. When we put these pointy brackets, the way we read that is the group generated by F and G. That means that you can write any word, any string of letters with F and Z's, F, F, G, F, G, G, F, 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 and all of those elements will be in S3, except you get to simplify them using these relations as we discussed. So whenever you see 3 F's together, they go away. Whenever you see 2 G's together, they disappear. And every GF, the F can be brought to the front, but with a cost, the cost being that the F becomes F squared. So using that, any word can become F to a power, G to a power. And that power for F can be either 0, 1, or 2. And the power for G can be either 0, 1. We have a lot more to say about symmetric group, but those will be a subject of later lectures after we start formally studying groups and have some techniques and tools to actually get our hands dirty and learn a lot more about these groups. So next is going to show you that S4 has a subgroup isomorphic to D8. And if you don't know what those things mean, that's why you should be watching the video. And this is the end of this lecture, and I will see you in the next lecture.